So, welcome to this class on hardware security. So, we shall be continuing our discussions on infective countermeasures for differential fault attacks. So, in today we shall be discussing about few attacks, like we already started discussing about an attack against a potential infective countermeasure using a constant fault model. So, we shall be trying to see how we can extend this to even attack the entire state matrix, which we did not or could not attack in the last day's discussion. We shall be discussing about how to perform an attack using a random fault model, which makes the attack more generic. And then finally, we shall be discussing about some modifications to the countermeasure which should be able to protect against these kind of attacks. So, to start with, this is a quick reminder of the infective countermeasure. The infective countermeasure essentially has got 3 rounds. Apart from the cipher round, there is a redundant round and there is also a dummy round which comes in spuriously. So, the idea is that it's a kind of repetition of sequences of redundant cipher and so on, but there are also intermediate dummy rounds which are indistinguishable from the redundant and the cipher round, and therefore, it becomes very difficult for the attacker to know when to induce the fault, because the dummy round kind of confuses the attacker. At the same time, because of the way the algorithm or the countermeasure has been developed, right, if there is a fault either in the redundant round or in the cipher round or even in the dummy round, then it basically infects the following operations, and finally, right, it results in a cipher text which essentially cannot be exploited, or which is supposed to be not exploited by the adversary, or at least it makes it more difficult for the adversary to exploit. So, the whole idea is that it tries to make the differential of the fault or the differential of the output faulty cipher text as uncorrelated to the secret key as possible to rule out a possibility of a differential fault analysis. So, therefore, right, of course, we have seen few points in the last class, like there is the rounds and the ciphers and the redundant cipher, the actual cipher round and also the dummy rounds are constructed in a way so that they are equivalent, so that they cannot be distinguished by also other side channel techniques like power or electromagnetics, so that it becomes difficult for the attacker to induce a fault at an opportune location. So, here is a quick reminder of the attack that we saw in the last class, and we saw that if there is a fault, for example, here the fault is at this location or at this byte of the state matrix, and this fault is at the input of the 10th cipher round, then what happens is, because of this fault, right, the fault essentially gets affected here, so and it basically affects R0. So, R0 essentially stands for the actual computation or the cipher round. Now, because of this fault, the fault essentially means that the fault basically propagates through the round of through the 10th round, and therefore, it gets shifted, of course, after getting modified by an S box, and therefore, right, if you assume that one of the correct state is I110, so I110 stands, for example, the first byte of the 10th round input. For example, the 10th round input is say denoted as like this is the 0th byte, this is the first byte, this is the second byte, and this is the third byte, and so on, as we have seen in previous classes. So, if I take one of the states as I110, that means the correct state as I110, then because of the fault, this gets affected as I110 and becomes I110 XORed with F. So, now if I considered both the the correct operation, that is the correct execution path, and also the faulted execution path, then the differential at the output of the S box would be basically captured by, say, epsilon, where epsilon stands for the XOR of S of I110 XORed with F XORed with S I110. But at the same time, always remember that there is also a shift row, and because of the shift rows, what happens is that this particular byte gets shifted to this location, and now there is an interesting thing which happens. So, this is essentially a usual encryption process for AES. Now, when we consider the countermeasure, then there is an additional thing which happens accordingly. So, what happens here is that because of the presence of this function which is called as SNLF, what we measured is the XOR of the redundant and the cipher round, and we know that XOR right now stands as epsilon, because the rest of the bytes are same in both cases of R0 as well as in case of R1, that is in both cases of redundant round and cipher round. Remember that the 10th round redundant round has already taken place. Okay, so the sequence is redundant cipher and so on. And so if we are inducing a fault at the at the 10th round cipher, then that means that the 10th round redundant operation has already taken place without any error. So therefore my reference point is correct, that means my R1 stands for my reference point, and what essentially we are basically comparing with in R0 is basically the cipher but with the fault, and the fault in this case is epsilon. So now what happens is, because of this XOR I get an input of epsilon, and that gets converted into SNLF epsilon. As we know that SNLF function, if there is a non-zero value, then it also produces a non-zero random output or random looking output, and that essentially pollutes both the cipher as well as the dummy round. So if I consider, for example, the cipher, right, then what happens is this gets further polluted with epsilon. It was already there, it gets further contaminated with SNLF epsilon, and therefore this disturbance becomes epsilon XORed with SNLF epsilon. Now if you look at the dummy round infection, then this SNLF epsilon also affects the dummy round, and you note that the dummy round was initialized at some beta value. Suppose like I have got beta 0, beta 1 and so on, this is beta. But now because of this infection which happens in the dummy round as shown by this equation, so this particular diffusion is basically that what you basically do is you apply the round function on R2 comma K0 and you XOR with beta. So note that if R2 is beta, then this value also computes to beta, and therefore you get beta XORed with beta, and that is 0. But now because of the fault, all 15 bytes have got the same bytes as that of beta, but this byte is different, and this byte, right, is kind of contaminated with again this error which stands for SNLF epsilon, and therefore, right, we basically have this additional error which we need to kind of accommodate. Now remember, the round function is nothing but an usual AES operation, and therefore, right, what will happen is that this particular byte will get distributed into this column, but again there will be a further shift, and we know that the shift which happens, right, because of AES round computation is a shift for, like in the second row there is a shift to the left by one position, and therefore, right, this column comes here, and then there is a mixed column which comes in the round function, and that spreads this disturbance to this entire column, and therefore this column becomes something like delta 1, delta 2, delta 3 and delta 4. And now this particular disturbance, right, affects your actual cipher round. So therefore if you go back and see the equation in the infective countermeasure, then this is the line that I am talking about. You see that this particular XOR is XORed with R0, which is your actual cipher, which is essentially returned as your computed cipher, and therefore, right, what will happen over here is that because of this, like the original cipher will also get further contaminated, and you will have this particular disturbance as a result. Now the interesting thing is that because of this shift, this particular pollution affects the third column, okay, whereas this disturbance which stands for epsilon XORed SNLF epsilon gets exposed to the adversary. So if the adversary basically measures the XOR of the faulty output, which is essentially nothing but the faulty R0 value, and XOR it with a correct computation, and then he can basically get this differential, and therefore, right, he can easily know what is the value of epsilon XOR of SNLF epsilon, where epsilon stands for this value. So now how can so this basically leads to an attack, and because of this, right, essentially what the attacker will try to do is the attacker will now, and this attack, right, would work pretty much on all the last 3 rows of AES, because in all of them, right, because of this shift, this particular disturbance will get exposed to the adversary. I will emphasize later on that if this fault is happening like at the first row, then this will not happen, and then because because there is no shift in the first row of the AES state matrix in when we are considering the AES round. So now what will happen is essentially here shown here. For example, we as I said that epsilon is related with S of I110 XORed with F XORed with S of I110. What I would try to do is basically I will try to get the value of this I110. Remember, this I110 will basically in turn give me a value of this key byte, because this key byte will basically get kind of processed with this particular, will essentially will get leaked because of this fault. Of course, right, in order to get the actual value of the key, you have to probably take more pairs of faulty and correct cipher texts, and again using a constant byte fault model, we can essentially retrieve the corresponding key. Now why constant fault model, or how will the attack exactly work, is illustrated subsequent to this. So here we see the process of retrieving the key. So what we do is that we basically try to guess this key byte. So remember that this key byte, like this particular key byte, for example K13, can take 0 to 255, that means 256 possible values. So if I do that, then what I will now do is I will kind of invert and compute S inverse and XOR C13. Remember that C13 would stand for a specific location in the cipher which get XORed with this key byte, and then compute the inverse of that. So this essentially is nothing but I110. So one of the reasons, right, why there is a relationship between this key byte and the I110 position is quite straightforward, because you can observe that like the key byte that is there, like if you consider the state matrix, then I am talking about this position in my essentially is referred as like I1, and 10 essentially stands for the round. So one of the reasons why we use this along with this key byte is because of the shift rows operation, and you can observe that if you consider the shift row subsequent to this, of course there is an S box also, then this particular byte will get left shifted, and therefore this will come to this location, and again therefore like this will get basically combined with this K13, okay, and will result in your ciphertext C13. So if you basically would like to work backward, then that means that if I would combine C13 with K13, compute the S inverse to get this particular byte which stands for I110. Okay. So therefore with this like perspective, one can easily understand that this is correct, that I110 is equal to S inverse of C13 XORed with K1311. So now what we do is we basically guess this error. Note that the error can be anything except 0, because if it is a 0 then it is not an error. So there are 255 possibilities, and what we do is basically we compute epsilon, which stands for S of I110 XORed with F XORed with S of I110. Okay. So epsilon, as we know, right, is equal to S of I110 XORed with F XORed with S of I110. So now what we do is basically, right, I mean we already can compute this because we have basically estimated the value of I110. We basically make a guess for this error and then we compute epsilon. But now we also have this value of epsilon XORed SNLF epsilon, which has been exposed to the adversary because of the attack that I just mentioned and because of the observation that I just mentioned. Therefore, right, if you basically get this value, then what you can do is basically you can check whether indeed like the XOR of C and C13, because you can take the XOR at the position in the ciphertext and you can check whether this computed value of epsilon satisfies this equation or not. So what is the chance of a particular thing getting like satisfying this equation? I will come to that, but first observe that the possible number of guesses that you are making is K13, there are 256 choices, that is 2 power of 8, and there are 2 power of 8 minus 1 choices for F. So therefore total there are around 2 to the power of 8 into 2 to the power of 8 possible choices for the tuple of F and K1311. And what is the probability that a random equation will satisfy this equation? So suppose I make an assumption, which is essentially also stated in the paper, that SNLF epsilon stands for like the finite field inverse, and if that be so, then there are approximately like 2 solutions which will probably satisfy, because you can observe that the equation is like epsilon plus 1 by epsilon. So that means if epsilon satisfies the equation, then 1 by epsilon also satisfies the equation. Okay. So what I am saying is that if you basically say that, and similar things can be also observed for other nonlinear function. So if your SLNF epsilon is nothing but 1 by epsilon, that is the finite field inverse, then the equation is epsilon plus 1 by epsilon is equal to some constant value, okay, because this value is already observed from the cipher and from the faulty cipher. So here if epsilon is a root, then 1 by epsilon is also a root of this equation, okay. Therefore there are 2 solutions, and there are 2 power of, and the probability of this equation getting satisfied is therefore 1 by 2 to the power of 8, because like this value is already known from the output, and the probability that a random choice will satisfy this equation is 1 by 2 power of 8, because there are 2 power of 8 bytes, and out of them I am considering 1 byte. Actually it is not one value, but there are 2 values which can satisfy depending upon the value of your epsilon, okay. So therefore, right, I mean roughly speaking, like you will have, if you consider this, then approximately 2 to the power of 9 values will survive and will basically kind of satisfy this equation, and you can see that this is nothing but, if I multiply, then it is 2 to the 2, if I multiply this probability with this, then 2 to the power of 8 gets cancelled with 2 to the power of 8, and you have roughly 2 into 2 to the power of 8, which is 2 to the power of 9 key fault pairs which survives this test. Now what I will do is, therefore, I will repeat this error, test, okay, by using the same error. Note that if I kind of vary the error, then this attack will not work. So I keep the same error, and therefore the error is constant, and I repeat it for 3 pairs of ciphered and faulty cipher to obtain a unique value of the key byte. So this attack can be pretty much kind of extended for the other byte positions, and therefore we can essentially perform a fault attack in this particular model. So now the question is, right, I mean, so basically, like if I summarize, what we have seen is that the last cipher round, and you know, like the reason why it works is because the last cipher round is always the penultimate round. Remember that when the final, you know, like round comes before the final compulsory dummy round, which is the 15th line in my algorithm for infective countermeasure, then you will find that the last round is always a ciphered in this case, okay, and therefore the attacker can verify the target round using side channels, because it can probably know when is the penultimate round which is happening, and therefore can for certainty kind of say that this is my you know, like 10th round being in operation. Likewise, right, what we observe is that if there is a fault in the last 3 rounds of 10th round, then the infection caused by the compulsory dummy round does not affect the erroneous byte, because of the shift, right, because if you see that if there is a fault, then what is happening is that this particular byte is not getting affected, because this diffusion is getting shifted, okay, and therefore the attacker has an access to the output differential. So now the question is, what happens if the infection caused by the compulsory dummy round affects the erroneous byte of 10th round, okay, and actually, you know, like more importantly, like suppose, you know, like this particular attack happens in the top row, then what will happen? So the fault F in I010, that is the first byte of the top row in the input of the 10th cipher round, is now where the fault is seated, and we can easily understand that, you know, like that because of this, the countermeasure infects the faulty computation twice, after the execution of the 10th cipher round, like in the previous case, and again after the execution of the compulsory dummy round. So this is something, or this attack propagation is similar to what we have already seen. The only thing is that the fault location is now in the first row instead of the second row, as we have seen in the previous illustration. So therefore, right, if the fault is here, then again similar things will happen, and but there is a small difference that will also happen, which is essentially important. So here this difference will result in, suppose, alpha 1, alpha 2, alpha 3 and alpha 4, but remember, right, this does not get shifted, because in the first row there is no shift, okay. So this basically gets also in the first column, this is also in the first column. So when you XOR it, this particular difference, that is epsilon XOR SNLF epsilon, which we exploited in the previous attack, is not known to the adversary, because it gets masked by this alpha 1, which is seemingly a random component. And therefore, right, it is difficult for us to extend the FDTC attack to the top row, or, you know, like, and it was claimed that the attack will probably not work, because alpha 1 has to be masked, or, you know, like alpha 1 has to be unmasked rather, to get the value of epsilon XOR of SNLF epsilon. But now we show that all these alpha i's, like alpha 1, alpha 2, alpha 3 and alpha 4, are actually interrelated, and therefore you can remove their effect and obtain the value of epsilon XOR SNLF epsilon. How can you do that? Essentially because of a major flaw in the infection scheme, okay. So if you remember again the 15th equation that we had, so there the important step that we did was we basically corrupted R0, that means in the compulsory dummy round, we basically corrupted R0 with the XOR of beta and the round function applied on R2 and K0. Remember that if, right, the R2 or the value of R2 is beta, then the round function results in beta, because this round function or the dummy round was idempotent with respect to K0, and therefore a beta input was resulting in a beta output. But now imagine that R2, because of some kind of pollution, is not equal to beta, then what is the result of this computation? So you can easily observe that this round function can be broken up into the AES components, which stands for the S box, followed by the shift row function, followed by the mixed column operation. And that applies for both these round functions, because they are exactly same. So here, right, this operates on R2 comma K0, whereas this operates on beta comma K0, and you can therefore write this operation as MC SR S applied on R2 XORed with K0, which is a round key, XORed with again MC applied on SR, XOR applied on S of beta, XORed with K0. Now this K0 and this K0 gets cancelled, and note that mixed column and shift rows are linear operations, and therefore I can again take them in common, and what I have here is S of R2 XORed of S of beta, which I cannot combine because the S function is a nonlinear function. But then we observe that if R2 is equal to beta, then these two things will be same, and therefore this result will be 0. So you will have exactly what you want, which is essentially 0 in this case, and therefore there is no further propagation of, or there is no contamination which happens because of this. But if R2 is not equal to beta, then this value will result in a non-zero value, because R2 and beta not being same, S of R2 and S of beta will also not be same, because the S function is bijective in case of AES. So therefore, right, what will happen is that suppose the fault is in the first round, and therefore, right, we are now considering the diffusion in the dummy round. So remember, right, the fault is over here, which is essentially standing for SNLF epsilon. So if we just observe the depiction here, the fault is here, right. So this is the fault, SNLF epsilon. So now because of this like round computation, what will happen over here is that the round function R2 comma K0 XORed with beta will be essentially as shown previously, the mixed column applied on shift rows applied on the XOR of S of R2 and of S of beta. So this is your like disturbance. So if we apply the S function, then this gets converted into some unknown value, and again because of shift row this does not get shift, because in the first row there is no shift. Now we apply this mixed columns, and because of this mixed columns we again get this like interrelationship, as we have seen in the context of DFA on AES. We get relationship which is like 2y, y, y and 3y. So that, what does it mean? It means that if, right, the attacker observes the XOR of the correct and the faulty ciphertext, then the alpha 1, alpha 2, alpha 3 and alpha 4 that we were seeing previously are not actually random. There is a relationship between them, and that means that if the attacker observes this disturbance, for example, the attacker knows the value of y, and if the attacker knows the value of y, the attacker can also know the value of 2y, and therefore from there can unmask this contamination and again get the value of epsilon XOR SNLF epsilon, and therefore can pretty much repeat the attack that we just now saw on the remaining 3 rows of the AES state matrix. Therefore, right, this attack will work pretty much on any of the byte positions. Okay. So therefore, right, this is an illustration of how the attack works, and it will probably work even over here, because you can remove this disturbance and get the value of epsilon XOR of SNLF epsilon and repeat the attack. But again, right, as we discussed, that this particular attack requires a constant fault model, and therefore, right, what we expect is a kind of like assumption that the fault essentially every time when you are repeating the fault is a constant fault. However, right, what we would probably like to do is basically we would like to apply the classical DFA on this countermeasure, where we would like to assume that the fault is a random byte fault. So if we assume that, then like again we will basically assume here that the fault is inflicted in the penultimate round of AES, that is in this case of 128 AES at the input of the 9th round, which we make as a target. So the fault F is in I0n, so I0n stands for here, and therefore the faulty state matrix at the input of the 9th round is shown in this state matrix, where everything remains the same except this particular byte, which is contaminated with a random fault. So now we make an assumption, or we start with an assumption which we will relax subsequently, is that there is no dummy round after this fault injection except the final compulsory dummy round. Okay. So we basically make an assumption that there is no like after the fault induction except the final compulsory dummy round, there is no dummy round that happens. Okay. And that implies that like if you are inducing the fault, for example here, and the fault is at the input of the 9th round. Okay. So that is where I would like to induce the fault, but what may happen is that like since you are doing a cipher operation here, that means there is a previous redundant round which has already taken place. That means after this, right, there will be again a redundant 10th round operation followed by again an 11th round, the final 10th round cipher which takes place, and here there is a compulsory dummy round. Okay. So this is the compulsory dummy round which takes place. So therefore, right, what will happen is that this countermeasure will infect the, so if you are able to induce the fault indeed at this position, then that means the fault will kind of infect, or rather there will be an infective infection in the computation in 3 locations. Okay. So the one is of course like after the execution of the 9th cipher round, one is at the after the execution of the 10th cipher round, okay, and you will basically get the fault also at the like after the execution of the compulsory dummy round. So these are like the positions where you will essentially have the fault which is essentially created. Remember that you will not have the fault here because, or you will not have an infection when you are doing the redundant computation, because in our particular example, right, we basically do the check that whether there is a difference between the redundant and the cipher round, and we basically contaminate only after the cipher round. So we do not do that check after the redundant round, and therefore, right, this error will not kind of infect after the redundant round. Okay. So where will that infect? This will basically get infected only after the cipher round. Okay. So this I believe can be easily observed, right, if you go back and see the algorithm. So in the previous case, right, if you just walk back a few steps and take a look at the original algorithm, right, I mean this becomes quite clear. So for example, if you observe this algorithm, then this infection, that means the infection of computation of error epsilon, which is SNLF of C0 XORed with C1, only happens if I is even, okay, and I becomes even. So we start with I equal to 1 and then we have the even term. So that means the second term is always the even term. Okay. So that means, right, this check happens only when you are doing the cipher computation and not when you are doing the redundant computation. Okay. So that means, right, if you are inducing the fault at the 9th round cipher, then the infection will happen subsequent to this, not in the 10th round redundant round, but in the 10th round cipher. Okay. And therefore, right, we will have the fault indeed at these 3 positions or 3 instances, which is essentially after the execution of the 9th round cipher, after the execution of the 10th round cipher, and also after the execution of the compulsory dummy round. Okay. So next class, right, we will see that how we can use this setup to perform an end-to-end attack on this particular countermeasure and show that it can be completely broken. Okay. So thanks for your attention.